Hello and welcome as we begin a new topic, or rather revisit the topic of equilibrium, picking up from where we left off and extending our understandings a little bit further. Looking today at the concepts of pH and the acid dissociation constant, where we're going to investigate pH, a number of equilibrium concepts there, and how to utilize these in calculations. So to begin with, let's recap some important topics that we've previously visited, but we can revisit now, that are going to be necessary for our understanding as we extend equilibrium as a concept. So the first one was the Bronsted-Lowry theory of acids and bases, and this states that acids are defined as proton donors and bases are defined as proton acceptors. There'll be a few different ways to define your acids and bases, but we're going to be primarily concerned with the Bronsted-Lowry definition. And then the other concept was the idea of conjugate pairs, which is an acid and a base on each side of an equilibrium equation that are related to each other by the difference of a proton. So we have the equilibrium, implying the reversible reaction at equilibrium, rates of the forward and backward reaction equal each other, and the concentrations of reactants and products remains constant. So look, let's have a look at these definitions here. So I've just designated A for acid, B for base. These aren't actual chemical elements, but they're just showing that acids are our proton donors. So we have that hydrogen there that can be donated to the base, and we end up with the conjugate pair. So we can see that the acid and its conjugate base are related to each other by the difference of a proton, where the acid has lost a proton. And then the base, with a lone pair of electrons, can accept the proton, and we end up with our conjugate pair on the other side. So notice that the acid becomes a conjugate base, because when we consider in this backwards direction there, well, this has now become a species which is a proton acceptor, where it was a proton donor. Once it's donated that proton, if the backward reaction can occur, it's then going to be able to accept a proton, all linked to this idea of the conjugate pair. Similarly with the conjugate acid, the base was a proton acceptor. Once it's accepted the proton, if that backward reaction drives, well, then it's then donating it, so it's the conjugate base. So these two ideas of conjugate pairs and the Bronsted-Lowry theory of acids and bases that we can practice now. I've got a reaction there, acid-base reaction. For the reaction below, label the acid, label the base, label the conjugate acid and the conjugate base, and identify the conjugate pairs, similarly to how I've done it there for that generic example. Pause, and let's have a look. All right, well, what are our conjugate pairs? That species is differing by the difference of a proton, and those species are differing by a proton. Now we've got to assign the acid and the base. Which one is donating the proton? Which one is accepting the proton? Well, going from NH3 to NH4, obviously it's gained a proton. So that's going to be our base, which means that our H2O going to OH-, it's lost a proton. So that's going to be our acid. So we can go ahead and label everything accordingly. So the base becomes the conjugate acid, the conjugate pair there, differing by a proton. The acid becomes the conjugate base, differing by a proton there. Brilliant. One final recap is the idea of an equilibrium expression, then we'll dive into some new stuff. Equilibrium expression, which is given this symbol Kc, a relationship that links the equilibrium concentrations of reactants and products to the stoichiometry. And from the equilibrium expression, you can calculate an equilibrium constant, where your value of your equilibrium constant is going to tell you where that equilibrium is sitting. The larger the value, the more it's sitting to the right-hand side, the more it's favoring the products. The lower that value, the more it's favoring the reactants and sitting to the left-hand side there. So let's remind ourselves about this one. We have some sort of generic equation. A plus B goes to C plus D. So it links the concentrations of reactants and products where we put the products. So you can think of it as the concentration of the products over the concentration of the reactants. But the stoichiometry is going to play a part, so that needs to be accounted for as well. So look, if we've got species C and D, this is just a generic example, we've got all sorts of different types of reactions. You know, you might have only one thing on one side of the equation, you might have 3 or 4 things on one side of the equation. You include all of them, the concentrations raised to the power of their stoichiometric coefficient there, and then do the same, it's products over reactants, so do the same for the reactants on the left-hand side. So this is what we're saying about that value. If our equilibrium's a large number, where we've got more products of that's bigger than our reactants, we're obviously going to end up with a larger value there, which is above 1. And if we have more reactants, can I get rid of that? I can. If our bottom number is bigger there, then it's obviously going to be a smaller number, where if more reactants than products, we end up with a Kc value less than 1, which is very small. Brilliant. All right, so that's a quick recap of what we need going forward. Let's dive into something new, which is this idea of the ionic product of water. Now, it's a type of equilibrium expression. So we're given it this K symbol, but it's a little bit different. It's referring specifically to something to do with water. So that's why we're designating it with a W there for water. Water is an amphoteric substance. We've defined that previously as something that can act as either an acid or a base. Depending on what it's with, what the context is, it's able to accept a proton, but it's also able to donate a proton, where water is very much an example of an amphoteric substance. So let's consider, let's show it. So, we've got H2O here. Let's just say it's reacting with another H2O. Well, if we define all of our conjugate pairs, we could say that's a conjugate pair, differing by a proton. We could say that's a conjugate pair, it's differing by a proton. Now a H2O to H3O plus, that's accepted a proton, so that would be acting as a base. Whereas a H2O going to OH minus, that's donated a proton, so that's acting as an acid. It's water, both a H2O, it can act as either an acid or a base, so we can say it's amphoteric. We could label the conjugate acid and the conjugate base accordingly. We can simplify this equation, however, showing it as a dissociation of water. And this is primarily what we'll be showing it as, just because it's a little bit more simplified, left to right, where we've got H2O going to H plus OH minus, where our H plus is fulfilling the same role as the H3O plus there. All right, what would a Kc expression for this reaction look like? That'd be a good one to give a crack. I've given you a general idea of the Kc expression. What would it look like for that one that is highlighted in blue? Why don't we build it together over here? So our Kc for this expression is the products. Maybe I'll write it up here. H2O going to H plus. I'm really bad with my states. I always forget my states. Don't you forget your states. Like so. So we're going to have the concentration of H plus times by the concentration of OH minus. Stoichiometric coefficients are equal to 1. So to the power of 1 is just going to be itself. So let's not worry about doing that. Let's just keep them like that. Over the concentration of water. So that would be our Kc expression there. So I'll get myself out the way. We'll have a look at that. However, the extent of ionization is incredibly low. Therefore, H plus and OH minus is 2. Oh, is 2. Sorry, I thought that was a sentence I didn't finish writing. 2 is in also. So what are we saying? Extent of ionization is incredibly low, therefore the concentration of H plus and OH minus is also incredibly low. So we can simplify further. We can assume that the concentration of water is constant. So we can turn this Kc expression into a Kw expression by ignoring the concentration of water and just having it equal to H plus times OH minus. And this gives us our ionic product of water. It's the equilibrium constant for the ionization of water. Why is this important? Well, this is important because it is a constant value at 298 Kelvin. So it's that value, 1.0 times 10 to the minus 14 with these units at 298 Kelvin. So let's recall with our equilibrium expression, what we need to do is we need to determine units by cancelling out our units of concentration and working out what we've got each time. So we don't necessarily have a consistent units for concentration, but let's look at deriving them now. So let's say if we've got a Kw expression, which is H plus times OH minus, if we say that concentration of water is constant, well, we're going to have units. We've got a mole per decimeter cubed, and we're going to multiply that by a mole per decimeter cubed because these both have the same units. So that gives us a unit of mole square, decimeter cubed. That becomes decimeters to the minus 6. We can add those powers with our power laws. Look, so that'll be our units of Kw. Now, pure water is neutral. So what this means, if we think of acid as a proton donor, base as a proton acceptor, Well, if it's neutral, we have to have the same amount of these. So that means that our concentration of H plus is equal to our concentration of OH minus. So up here, if H plus equals OH minus, that means that pure water, we have concentration of H plus squared to calculate that, because it would be H plus times H plus if we say that those two are equal. So therefore it's going to end up as the square of it. So we can rearrange this to work out what the H plus of water is. Because we know the Kw, we can rearrange this equation to get the concentration of H plus equaling the square root of Kw. And then as we have a value for Kw, which we just said was our value over here, 1.0 times 10 to the minus 14, 1.0 times 10 to the minus 14. If we calculate that, that'll give us our concentration of H plus in pure water. So we do that, Kw is equal to H plus squared. If they're equal, punch that in and we get a value for the concentration of H plus in pure water being that many moles per decimeter cubed. Now this would also imply that that's the concentration of the OH minus, because remember in pure water, our amount of H plus and OH minus are equaling each other. Brilliant. So that brings us to pH. pH, I'm sure it's something you've seen at least in passing, a very commonly used scale to measure acidity and basicity of a solution. And up until now, you've just sort of been told that it's measured on a scale of 0 to 14, with 7 being in the middle. And you might have asked yourself, that's a strange scale. Why is that the case? Well, we can start to explain that with what we've looked at with the ionic product of water. So what makes the solution acidic? It's the amount of H plus in solution, because our acidity is defined as, proton donating, where a H plus is just a proton. So for it to be acidic, there needs to be protons available to be donated based on that Bronsted-Lowry definition. So it's a measurement of the acidity of an aqueous solution on a logarithmic scale. So, some people say it stands for power of hydrogen or potential of hydrogen. You're not really going to encounter those names. Let's just call it pH. And it's on a logarithmic scale where we can multiply it by our concentration of H plus, and we've got a negative sign there as well. So we use this logarithmic scale because there's a huge range of concentrations for hydrogen ion that we can have that we'll look at in a moment. And what it does, what we use all our logarithmic scales for when we look at them in chemistry, it just sort of squishes it all together, gives us a nice usable scale. So let's consider this scale. I might go over here and I might redraw with my fancy line tool. We'll redraw a pH scale. So we've said it's gone from 7 in the middle, goes from about 0 to 14. So let's consider what we just said about a pH of 7, where a pH of 7 has concentration of hydrogen ions equal to the concentration of hydroxide ions. Well, we just calculated how much hydrogen ions are in a neutral solution, and we said it was equal to 1.0 times 10 to the minus 7 moles per decimeter cubed. I'll just pop a capital M there for my space. So let's calculate the pH at this neutral solution. We said it's the minus log times by the concentration of H plus, where we've just said the H plus is that value there. Grab your calculator, double check, don't take my word for it. You plug that into a calculator, you get a pH equal to 7. Let's say we've got something that is very acidic. Let's say we're dealing with a 1 mole per decimeter cubed solution of hydrogen ions, a very acidic solution. Let's go down here and let's calculate the value of that. So minus log of H plus, if we say that's 1 mole per decimeter cubed, again, grab your calculator, don't take my word for it. You get the minus log of 1, you're going to end up with 0. So that's incredibly acidic, 1 mole per decimeter cubed. And then if we go at the other scale, let's say we've got, I might just put these values down here. We said 1 times 10 to the minus 7 moles per decimeter cubed. Let's get a very, very dilute, what would be a very basic solution. So let's do the pH equals the minus log of our hydrogen ion concentration. Let's say we've got something very dilute, 1 times 10 to the minus 14 moles per decimeter cubed. Again, logarithm rules. I mean, a lot of you will be able to do these logarithm rules in your head if you've gone through them in maths, but I like to just make sure in the old calculator. we've got a pH of 14 there. So again, starting to explain why we've got this scale from 0 up until 14. It's measuring the concentration of hydrogen ions with that reference point in the middle, with our concentration of hydrogen ions in a neutral solution being that many. All right, so it shows how acidic or basic a solution is from a scale of 1 to 14 or 0 to 14. You can get negative values, but you won't encounter them too often. Invented by, oh, fantastic name, my favorite name of all the chemists we look at, Danish chemist Søren Sørensen. Sorry if I've mispronounced my Danish O with a line through it there. But it uses a logarithmic scale to account for that very large range of hydrogen ion concentrations. So, let's consider going from a 1 mole per decimeter cubed solution to a 1 times 10 to the minus 14 moles per decimeter cubed solution. That's a huge range, even just going from 1 to neutral. That's a really big range. So our logarithms, that power of 10 conversion allows us to squish it all together and have a nice, usable, relatable scale. Negative sign gives us mostly positive values for our pH, just again, because of those logarithm rules. Again, really, really acidic, high concentrations of acids, you can get negative values as well, so be aware of that. And our pure water is neutral, so thus that central point that we just calculated, 10 to the minus 7 moles per decimeter cubed, based on our pH scale, pops us in the middle at 7. So in an acidic solution, we have a concentration of hydrogen ions greater than a concentration of hydroxide ions, for all those reasons we've been talking about. In the neutral solution, the hydrogen ions equal the hydroxide ions, and in the basic solution, the hydrogen ions are less than the hydroxide ions. The hydroxide ions are more than the hydrogen ions. Two ways of saying the same thing. Now we can rearrange this calculation, again using logarithmic rules, to make the H plus as the subject, wherein you can calculate the H plus concentration as being 10 to the minus pH. Let's practice that now. I've got 2 questions here. One asking you to calculate the pH using that equation. One asking you to calculate the H plus using that equation. Have a think about it, pause. Just a bit of a plug and play using our fancy new equations. Let's go through some answers here together. So our first one, we were being asked to calculate the pH of a solution, which we know is equal to the minus logarithm times by the concentration of H plus. So that's going to be equal to the minus log times by our value, which is going to be 1.6 times 10 to the minus 4, 1.6 times 10 to the minus 4 moles per decimeter cubed. Just plug it in the calculation, plug it in the calculator. 1.6 times 10 to the minus 4 gives us a value of 3.7958. So 2 significant figures. Let's say we've got a pH of 3.8 there. Let's ask ourselves what this means. It's less than 7, so that means we've got a acidic solution. Conversely, determine the concentration of hydrogen ions in a solution with pH equal to 10.5. Let's use our equation up here. We're going to end up with concentration of hydrogen ions equals 10 to the minus pH, where 10 to the minus, what was our pH value? 10.5. So we're in the basic region. 10 to the minus, 10 to the power of minus 10.5 gives us a value of 3.16. Let's use 3 significant figures that we were given in the question, times 10 to the minus 11 moles per decimeter cubed. So again, reiterating that idea that we've got a really, really large range of values for hydrogen ions. Look at the difference there. So we can use the logarithm scale to give us good pH values. Fantastic. What am I trying to do here? Trying to go over here. So there you go, 3.80 and then 3.16 times 10 to the minus 11. All right, let's investigate this acid-base strength and pH a little bit more. Let's consider strong acids. What do we know about strong acids? Strong acids completely ionize in the solution. So we have HA, we have the protonated acid. All of the acid goes to hydrogen ions and the conjugate base there. So for example, we have HCl, we're going to form all H plus and all Cl minus, completely ionizes, and we're going to look at monoprotic acids in this situation, meaning they just have one hydrogen ion, one proton. The proton, the hydrogen ion are referring to the same thing. So strong monoprotic acids completely ionize in water. Assume the concentration of acid is equal to the concentration of H plus and use that value in the pH equation. So this is saying that when we're using our pH equals minus log of H plus, we can just assume that our concentration of H plus is equal to the concentration of our strong acid because it's all ionizing, and because the amount of hydrogen ion from the water is so insignificant, from water dissociating, it's 1.0 times 10 to the minus 7. For all intents and purposes, we can just ignore that value. So when we're calculating the pH of strong acids, we can just use the concentration of the strong acid as the concentration of the H plus. We'll practice that in a moment. Just be aware that we're just looking for monoprotic acids. For di or tri or more generally polyprotic acids where they've got more than one proton to donate, a few more steps are required that we're not going to look at just now. Strong bases also completely ionize in water. If we talk about sodium hydroxide as an alkali, we have complete ionization, so all of the sodium hydroxide is going to make our hydroxide ions. So in this instance, we can calculate the pH by using our expression for Kw. Let's get some space down here. So our Kw expression, we said Kw is equal to the concentration of hydrogen ions multiplied with the concentration of hydroxide ions. Now Kw is a constant at 298 Kelvin, so that's really useful, 1.0 times 10 to the minus 14. So if we wanted to know the H plus, but we only got the OH minus, what we can do is we can rearrange this equation to make our concentration of hydroxide ions the subject. So that's just going to be Kw over concentration of H plus. What am I doing? Sorry. We want to rearrange this equation to make the H plus. I got distracted by someone out my window. H plus divided by Kw over the concentration of hydroxide ions. Now, the Kw is constant, so we have a value for that. It's a strong base, so we can assume that the concentration of our base is going to be equal to the concentration of our hydroxide ions. Let's have a look over here. So that's what we got here. We can rearrange the Kw expression, and we can, once we've got our concentration of H plus, we can plug it in Old Faithful to get the pH. pH equals minus log of H plus. All right, 2 ones to practice there. So the first one I've given you is a strong acid. So use our rules for strong acid up the top there. Second one is a strong alkali. Use our rules for our strong base down at the bottom there. And let's practice it now. So in this instance, we have the strong acid. And like we said, we can just assume that the H plus is all coming from that complete ionization of that strong acid. So we can just plug that in as the concentration for hydrogen ions. So minus log of 2.0 times 10 to the minus 3. Minus log times 2.0 times 10 to the minus 3. And that's going to give us our pH value here. Minus log 2.00 times 10 to the minus 3 gives us a value of, 2.6989, let's say 2.70. Which makes sense, we're dealing with an acid, so we're obviously going to be in the acidic region there. Now what about our sodium hydroxide here? Well, we've got to use the bottom method. We've got a strong base, so we first got to get the concentration of the hydroxide ions. So let's say if we rearrange the equation up here, so the concentration of H plus is going to be equal to our Kw value divided by our concentration of OH minus. Our Kw value is that constant up there, 1.0 times 10 to the minus 14. And then we're assuming the concentration of hydroxide is going to be equal to the concentration of the sodium hydroxide. You can think in terms of stoichiometry of these complete dissociations. 1 mole of that goes to 1 mole of that. So 0.0500. 0.0500. That gives us a concentration, good old calculator, 1 times 10 to the minus 14 divided by 0.0500 gives us 2 times, I should be consistent, we're given 3 significant figures there, 2.00 times 10 to the minus 13 moles per decimeter cubed. Not quite finished yet because we've now got to go ahead and calculate the pH. But as we're given a hydrogen ion concentration, we can simply plug that in our pH equation like so, minus log of our value up there, 2.00 times 10 to the minus 13, which is going to give us a value minus log of my answer there of 12.7. And again, makes sense, we're in that alkali region. So there you go, pH of 2.70 that we got up there, and then 12.7 for our one below there. Just a note, our pH doesn't have units there, so our pH is just a number. Excellent, so we looked at strong acids, strong bases. What about if we have weak acids? Well, let's remind ourselves what a weak acid means. The strong acid fully dissociated, weak acids do not fully dissociate, so they end up at an equilibrium, implying that we've got both the acid and the hydrogen ions and the conjugate base all in the solution there together. So what we can do is we can apply our equilibrium laws to get an acid dissociation constant, another type of equilibrium expression, so K, to do with acids, so the Ka value. Let's have a look at this one here. What am I trying to do that? Can apply equilibrium law to an acid dissociation constant, the equilibrium constant for a weak acid. So let's do that now. So let's say if we're getting an equilibrium expression, it would be the reactants, so H plus times A minus over our products, HA. And that is our acid dissociation constant. It looks like that. Now again, let's just focus on monoprotic, meaning they just have one hydrogen ion to donate. Again, we can assume that the concentration of H plus is going to be equal to the concentration of A minus, all shown in that stoichiometry there. You know, 1 mole of that will go to 1 mole of that and 1 mole of that. So as we did similarly earlier on, if we say that H plus equals A minus, then it's going to end up as H plus times by H plus over HA, which is going to be simplified to H plus squared over HA for our acid dissociation constant. Now, as all our equilibrium expressions do, the value of K implies which side of the equilibrium we're sitting and by how much. So our Ka value is going to imply the degree of ionization that our weak acid has. So from this, we can get the pH of our substances. So we want to rearrange, you know, if we need the concentration of hydrogen ions in order to be able to calculate the pH, we need to rearrange this one to have H plus be the subject of that equation. So let's do that now. So we said that Ka equals H plus squared over our concentration of HA. So if we need to calculate the Ka, we need H plus and HA values. If we're given the Ka and the HA concentration, then we can rearrange this to get the H plus value. So, you know, we would say that the concentration of H plus squared equals the acid dissociation constant multiplied by the concentration of our weak acid, and then therefore, do a little therefore sign, our concentration of H plus is equal to the square root of the product of these two variables there. If we have that, we can get a pH for our solution. Which is the next question that we're being asked. So we're given a Ka value for our weak acid, and we want to know what the pH is of a 0.15 mole per decimeter cube solution of this weak acid. So our pH equation, rearranging that one, give it a red hot try if you so choose. Let's go and calculate some values here. So look, we have our question and we've already rearranged our equation. So we want to get the concentration of H plus because we were given the Ka value and we were given the concentration of our weak acid there. So look, I rearranged it up there. So our value for Ka was given there, our concentration was given there. Let's plug and play and get some square roots of all that. So 6.3 times 10 to the minus 6 was our Ka value, multiplied by HA, which was 0.15. All right, plug it all in. 6.3 times 10 to the minus 6 times by 0.15, and I'll get a square root of that. We end up with a value of, no, what have I got? 9.7 times 10, I gotta count my zeros. 1, 2, 3, 4 times 10 to the minus 4 moles per decimeter cubed. And then from there, it's just a matter of plugging it in the pH equation. pH is equal to the minus log times our hydrogen ion concentration. We're gonna substitute in our value up there. The minus log of that gives us a value of 3.0. Let's go over here. Fantastic, value of 3.0. Now, what if we're given very weak acids? Well, the same way our pH is on a logarithmic scale, we can pop our Ka value, we can pop our acid dissociation constants on a logarithmic scale as well to get a pKa value. So Ka values can be very small, as we saw just here. We had a pretty small number there. In which case we can give a pKa value, which is just a value of Ka expressed as a logarithm. So if you've got the Ka value, you can get the minus log of that, and that gives you a pKa value. And again, the idea is it's just giving us some nicer numbers to deal with. So look, a final example, if you wanted to give it a crack. I've given you a concentration of a weak acid. Organic acids are often weak. And we've got a hydrogen ion concentration. So you've got to get the Ka value, and then from there, you've got to get the pKa value. Pause, let's finish this one off. So we said that our Ka is equal to that, so we can use that expression up there to calculate our Ka value first of all. So let's do that. So Ka is equal to the concentration of hydrogen ions squared divided by the concentration of the weak acid. We said that the hydrogen ion was that 1.32 times 10 to the minus 3. 1.32 times 10 to the minus 3, and we want to square all that, and we want to divide that by our weak acid concentration, which is 0.1. 0.1. This will give us the Ka value. Yet another one with the calculator. Minus 3, let's square that, and let's divide that by 0.1. So we've got, my calculator's not giving me in scientific notation, so I've got to count my zeros. 1, 2, 3, 4, 5 times 10 to the minus 5. Very small number. So let's go ahead and let's get a pKa value for this. So our pKa, well, that's not very legible. pKa is equal to the minus log of the Ka. We have a Ka value there, minus log of 1.74 times 10 to the minus 5. My handwriting is deteriorating as we speak. Minus log, oh, I pushed the wrong button. Minus log of the answer gives us 4.76 for a pKa values. There we go. So our Ka value of that, our pKa value of that. So, you know, our pKa values can be compared similarly to our pH values when we're looking at weak acids. Just a final quick note on Ka and the units. As with the equilibrium expression, we have to go and we need to determine the units for each of these as well. But if we have a look up here, if we have, you know, a moles per decimeter cubed, and then we got that squared, so times by a moles per decimeter cubed, and then we're dividing that by concentration, moles per decimeter cubed, they're going to cancel out, and in this instance, we're going to end up with a moles per decimeter cubed as the units for that Ka value. So don't forget those, as I did just before. All right, and with that, we've concluded this lesson, introducing these further aspects of equilibria. What do? We understand and use the terms conjugate acid and conjugate base, and we use these conjugate acid-base pairs to identify such in reactions, and we define mathematically the concepts of pH, Ka, pKa, Kw, and we use them in calculations. Tasks, pause if you like. You want some consolidation, one column at a time, working from the bottom to the top. Brilliant. Thanks for your time. Look forward to the next one. We'll continue looking at these equilibrium ideas that we've started investigating today. See you then. Have a good one.